Okay, this is just a quick summary of the most important aspects of principal components. PCA represents your data along a new set of variables, principal components. These are eigenvectors of X transpose X, where X is either a centered or standardized data matrix. Remember, to have an eigenvector, a matrix must be square. So be careful not to say the eigenvectors of our data matrix. That is a sentence that makes no sense because our data matrix is not square. So the eigenvectors of X transpose X, which is typically the covariance or correlation matrix. The data, once it's projected onto the principal components, is uncorrelated. Now, this actually means that the scores are orthogonal too. We haven't brought this up because I've given you a lot of information, but that happens to be a true statement. The variance that's explained by a principal component is given by the corresponding eigenvalue. When we have small eigenvalues, that means there's not much variance or information along that component. Typically, those principal components with small eigenvalues are the ones that we drop. That means that when we drop them, we project the data onto the span of the remaining components. The total amount of variance in data is given by the sum of eigenvalues. This is equivalently the sum of the variances of your original variables. So the sum of the eigenvalues is equal to the sum of the variances of original variables. Now, because that new data is completely uncorrelated, orthogonal, the covariance matrix is diagonal because the correlation between any two principal component variables is 0. And so the diagonal elements of the covariance matrix for that new data are just the eigenvalues because those are the variances of each new variable. So principal components is really just a matrix factorization, which gives you a new set of basis vectors and scores or coordinates for each observation. Now we can write this as a matrix product. Here I have V as the matrix of eigenvectors, those are principal components, as columns. S transpose is the matrix of coordinates for each observation. Now, if you're getting confused here, don't worry, we're going to illustrate this on the next slide. For covariance PCA, that data matrix contains centered data, and for correlation PCA, that data matrix contains standardized data. Now, this equation is the same as writing X equals SV transpose. You notice I have just taken the transpose of both sides of this equation to get the second one, right? Because of the reverse order law, when I take the transpose of a product, it's the reverse order of the transposes. Now, I'm going to illustrate this relationship here. The first one, when I write X transpose equals V times S transpose, I'm talking about the observations of my data in columns. Because most commonly, this is how we have liked to think about matrix multiplication, where each observation now is a linear combination of scores and loadings. Right? So this is this observation's coordinate along the first principal component, second coordinate along the second principal component. Now I have an approximately equal to here. Why is that? Well, because my data matrix, as shown, is 4 by 4, and so I should have 4 principal components. Since I'm only showing 3, it means that I have dropped one from this diagram. Now, when I write this equation the other way, this is how you like to think about the left-hand side of the equation, we like to think about our data matrix with the observations in rows, but in order to do that, you have to think about the coordinate basis representation in terms of linear combinations of rows, where the scores for observation 1 are in a row corresponding to columns that are principal components. Now, these diagrams may help you when you get into practice and you have to use a data matrix where the observations are in columns rather than rows for computational considerations. But other than that, I am not going to directly quiz you on this. I will just leave it to those of you who may need it in the future as a resource. The last thing I want to review is the difference between covariance versus correlation principal components. We use correlation PCA in cases where the scales of our data are drastically different. We use covariance PCA when our variables are on the same or similar scales. Remember, when we use correlation PCA, it is standardization that happens in the background. What does standardization do? Well, the typical statistical standardization makes it so that all variables have the same variance, which means that our method is going to try to explain all variables equally. And that may not be practical. That may not actually be what we want. Now, we can use other forms of standardization like range or min-max standardization to transform our data and then use covariance PCA. So this third bullet point would be an alternative to using correlation PCA when the scales are different. But it's important you realize that there's no mathematical relationship between covariance and correlation PCA. If someone gives me a set of loadings and scores from covariance PCA, I can't turn that into a correlation PCA. There's no mathematical transformation that gets me from the covariance version to the correlation version. I have to recreate the other PCA, find a new set of eigenvectors, etc. All right, so that's our quick recap. Now we can move on to factor analysis.